This is a pre-recorded talk for the state of the quantum universe. This is a review talk. In this talk, I'm going to give a brief introduction to islands and replica wormholes. So here are some references on this subject. The ideas come from, well, the ideas originate in the study of holographic entanglement entropy and this whole program. I'm not going to review that. It turns out that although it's a very good guide to the physics, that holography in the end isn't required. Then I'll talk about islands, which in particular these papers, and about replica wormholes. I refer people also, if you want to read something, to a conceptual review article that we wrote in June. So I want to motivate this with the page curve and the black hole information paradox. This is the Penrose diagram for an evaporating black hole. So here's the star over here. This is the point where it collapses into a black hole. Eventually there's a singularity. The black hole Hawking radiates. So these blue squiggles are supposed to represent the outgoing Hawking radiation. And the one point that I want to make here and emphasize is that Hawking radiation is a process of entanglement production between the black hole interior and the radiation. So this Hawking radiation is approximately thermal, but the full state of the quantum fields on one of these nice slices like this one here, the full state of the quantum fields on this slice is pure, and therefore the entropy coming from the thermal entropy of the Hawking radiation is entanglement entropy. The Hawking radiation is purified by modes on the interior. So those are these interior partners. So the black hole slowly evaporates. The Hawking radiation heads up here to future infinity. The black hole evaporates, and eventually the black hole is gone completely. At that point, the Hawking radiation is entangled with the entire interior. So to quantify this, we like to talk about the von Neumann entropy or fine-grained entropy of the radiation. The definition of this is written here. So we calculate the radiation at some distant location from the black hole, and calculate the density matrix rho sub r. That's the reduced density matrix of the radiation. This is a mixed state because the radiation is entangled with the interior. So it has some von Neumann entropy. It's important to note that this is fine-grained entropy. It's not the thermodynamic entropy that appears, for example, in the second law of thermodynamics. This is the fine-grained entropy, which would be invariant, constant under unitary time evolution. But in the case of an open system, like we have here, it can change as a function of time. So what we're going to do to discuss the page curve is to plot the fine-grained entropy of the radiation as a function of time. So according to Hawking's calculation, this is what it looks like. Hawking's calculation says that the density matrix of the radiation is thermal. So the black hole starts to evaporate. We collect that thermal radiation. The entropy just keeps going up until eventually the black hole evaporates away completely. At that point, it saturates and is just constant forever. So that's Hawking's calculation of the radiation entropy. And now we're going to see the paradox when we compare that to the entropy of the black hole. So the green curve is the area of the black hole divided by 4, so it's entropy. So the black hole entropy goes down as the black hole evaporates. And the paradox, the information paradox, as stated in terms of the entropy, occurs when these two lines cross. So the paradox occurs when the entropy of the fine-grained entropy of the radiation is greater than the entropy of the black hole. The reason for that is that remember we said that the von Neumann entropy of the radiation comes from entanglement with the black hole. Well, the area over 4 is measuring how many states there are in the black hole to be entangled with. So you can't produce more entropy from entanglement than the total number of available states you can entangle with. So you can make this precise, and this is a contradiction when these two lines cross. Of course, the contradiction is starkest at late times, where the radiation is in a mixed state and the black hole is gone entirely. But we can already see the contradiction as soon as these cross. In a unitary theory, Page argued that the actual entropy of the radiation should follow the dashed line. That is, it should go up at early times according to Hawking's calculation. But eventually, if we collect enough radiation, then the curve should turn over and start to go back down as required by unitarity. And in particular, that there would be a sharp transition here. And that transition is at the Page time. So the idea is that if we collect the early quanta, then eventually we'll notice that the late quanta are correlated with the early quanta. And as we see those correlations, we should see the curve go back down, since this is the fine-grained entropy. So to summarize briefly the recent developments, we now have a new calculation of the entropy, the entropy of radiation, that agrees with the unitary Page curve. The calculation involves two ingredients that I'll discuss in this review. First of all, it involves an island in the black hole interior. And secondly, it involves replica wormholes. So the calculation is justified by including replica wormholes in the gravitational path interval. A caveat that I'll come back to is that the gravitational path interval must be interpreted carefully. And I said we have a calculation of the entropy, but the way I would describe it, to be careful, is to say that this result is consistent with unitarity, but does not exactly demonstrate that evaporation is unitary. And I'll come back to what I mean by that after getting into the details of it. So first, I'll explain what islands are, also called quantum extremal islands. So islands come from what's now called the island formula for the radiation entropy, which is a generalization of the Ru-Takanagi formula. Here's the formula. So the idea is we're going to calculate the entropy of this region, the red region here, the radiation. This is the island formula. So let's unpack this a little bit. There's a gravitational contribution, area of, well, first of all, we have to include this auxiliary region called the island, the blue region. And then there's a contribution, which is area over 4 of the island. There's a contribution from the quantum fields on top of that, but it's not just the entropy. So this is an entropy of quantum fields, but it's not just the entropy of the radiation region. It's the entropy of the region island union rad. This means in particular that if we have a Hawking pair where we've collected one pair and the interior is in the island, then that pair will not contribute to this quantity because the pair taken together is pure. So we calculate this quantity. This combination is the generalized entropy. We calculate the generalized entropy. Then we extremize over the choice of island, I. Finally, if there are more than one extrema, we pick the one with the minimal value of the extremal entropy. This is the island formula. In some cases, there won't be an island. So in some cases, there won't be any, you won't find any extrema. And we would just say that it's the trivial island. You just take I to be the empty set. And if you do that, then you'll get back the usual Hawking answer for the entropy. But the general statement is that we have to allow for the possibility that there's an island here and to include it in our calculation of the entropy. So how does this help? Well, at late times, you can calculate the extremum, and the island is essentially just the black hole interior. So this point at the edge of the island moves onto the horizon, and the island covers the entire black hole interior. Therefore, Hawking radiation does not contribute to the second term. This quantum field theory term, remember, we said that if you have both pairs of an entangled pair, if you have both partners of an entangled pair, that will not contribute to this S because this is a fine-grained S, and together those two particles are pure. So this term essentially drops out, and what we're left with for S rad is just the area term. I is the black hole interior, so the area term is the black hole horizon area over 4. And this is exactly what we expected from the unitary page curve. As the black hole evaporates, this area term goes to 0, and we find that the S of radiation goes to 0 as it should as the black hole fully evaporates. Okay, so this formula was introduced motivated by holography, but in the end, we're going to see that it comes directly from the gravitational path integral, no holography required. Before we do that, I want to discuss also its interpretation. And some terminology. The edge of the island here is called the quantum-retrieval surface because this is determined by extremizing the generalized entropy. Good, so the interpretation. Well, if you're familiar with holography, then a quick way of explaining it is to say that the island is in the entanglement wedge of the radiation. If not, then let me explain it by saying that the island, that once you have the entropy formula, actually you get something much more than just an ability to calculate the entropy. What this very strongly suggests is that the island is actually encoded in the radiation, almost in the sense of a holographic duality. It's holographic, it's not holographic in the sense of reducing the number of space-time dimensions. The radiation here, if this is a two-dimensional black hole, then the radiation is two-dimensional, the island is two-dimensional. So it's not holographic in that sense. But it is holographic in the sense that the full quantum state, the quantum gravity quantum state of this region over here, the island, is supposed to be encoded in the density matrix of a system where gravity is not important. It's holographic in that sense. Operators in the island, like say a quantum field operator phi of x, where x is here in the island, can in principle be written as an operator acting on the radiation. This conclusion it almost follows as a theorem from the entropy formula. If this were a ordinary quantum system of qubits, then you can prove a theorem. Things are more subtle in this case, but we believe that this follows once you have the entropy formula. I won't give the argument for that, but basically if you have the entropy, then you can also calculate relative entropies. And if you can calculate relative entropies, you can reconstruct the states in the island. This decoding map that takes you from operators in the island to operators in the radiation can be very complicated and non-local. There have been a couple proposals for how to understand that. It's something that needs to be understood better. But the two proposals, one is called the PETS map, and the other uses the technique of modular flow. Okay, so now I'm going to move on to replica wormholes. So the island, as I said, was motivated by holography. It's a formula for the entropy that gives the correct page curve and is consistent with unitarity. But now the goal is to derive it. So we want to derive the island formula directly from the Euclidean gravitational path integral. To do that, we're going to use the replica method. The replica method is the following. We want to calculate the von Neumann entropy minus trace of rho log rho. Remember, rho sub r here is the density matrix of the radiation. But logs are hard to calculate with a path integral. So in the replica method, we instead introduce extra copies of the system. So n copies in total, where n is an integer. And we calculate z of n, the replica partition function, which is defined as trace of rho to the n. The advantage of phrasing things this way is that there's a Euclidean path integral that calculates this quantity. Once we've calculated z of n, under certain favorable circumstances, we may be able to analytically continue to n near 1 and then extract the von Neumann entropy by analytic continuation of the replica partition function. So if we're able to calculate this as a function of n and continue it to near 1, then we can extract the von Neumann entropy. The construction that I'll describe is general, but the complete details of all these wormholes and everything have been worked out only in some simple examples in 2-dimensional gravity. But I think the conclusion applies generally, including, say, to Schwarzschild in flat space-time, for example. So here's the basic idea. We're calculating in the replica method. Remember, we've introduced several copies of the system. So let's consider the case of n equals 3. So we have 3 copies of the black hole. We have 3 identical copies. And I've labeled the radiation region rad in each of them. Well, when you calculate trace of rho cubed in the replica method, dynamical wormholes appear connecting the black hole interiors. That is, there's a contribution to the path integral with the appropriate boundary conditions, which I'll describe in a minute. There's a contribution to this path integral where these 3 copies are not disconnected inside the black hole. They're actually connected through the black hole interiors. This is hard to draw. I've drawn it sort of schematically. These are actually complex saddles. You should think of them as instantons. They're space-time, complex space-time geometries that we can construct by explicit solution of the equations of motion for gravity plus matter in some simple cases, and can analyze also quite generally. In the replica limit, that is the limit n to 1, that's important for the von Neumann entropy, these saddles leave an imprint on observables, that is on your calculation of the density matrix, and they change the answer for the von Neumann entropy by a large amount and reproduce the island rule in the unitary page curve. Let's look at an example in a little bit more detail. This is the case n equals 2. So we'll imagine calculating with a path integral the quantity trace of rho r squared. Well, when we calculate trace of rho r squared, since we're doing a gravitational path integral, what we really do is we impose some boundary conditions, and then we have to ask which saddle points satisfy those boundary conditions. There's one obvious contribution to the path integral. The obvious contribution to the path integral with the correct boundary conditions is just 2 copies of the original black hole. You think of each of these pictures as producing a rho sub r, and this little bridge, the dotted lines connecting the 2 copies, these indicate that we glue the manifolds along the region rad. The reason for that gluing is because we have a matrix multiplication, rho r times rho r here. So that matrix multiplication is realized in the path integral by gluing together the 2 red regions. So we just have essentially 2 copies of the black hole glued along the radiation region. This I refer to as the Hawking saddle, because if this is the only thing you include, you'll get back Hawking's answer for the entropy and the non-unitary page curve. But the point is that there's a second contribution. The second contribution is the replica wormhole. This is another saddle with the same boundary conditions, exactly the boundary conditions that we use to set up this calculation of trace of rho r squared, where now there's this complex wormhole joining the interiors of the 2 black holes. So this is a solution of the theory, and it's one that we should include in our saddle point approximation to the path integral. Now let's think for a minute about which one of these contributions is dominant. So when we actually calculate the path integral, we're going to get something like e to the minus s, where s here has it has a gravitational action contribution, and it also has contributions from the quantum fields. So the first saddle, the Hawking saddle, gives e to the minus s2 Hawking. Then we sum over saddles. So the wormhole contribution is e to the minus s2 wormhole, and there could be additional contributions as well. Now, usually we think of the Hawking saddle as dominant, and that's the right answer at early times. This wormhole saddle has additional suppression coming from the fact that it's a higher topology contribution to the path integral. So that suppresses the path integral by something that goes as 1 over g Newton. On the other hand, this Hawking contribution here, this S2 is a measure of entanglement of the Hawking radiation with the interior. So this contribution, S2 is growing with T. S2 is growing in time as the black hole evaporates, which means that the Hawking saddle is getting exponentially suppressed at late times. Now the wormhole saddle is small, but it's constant in time. So what can happen, and what does happen, is that a time comes where the Hawking saddle is so exponentially suppressed that the wormhole saddle takes over and gives the dominant contribution to the calculation of this n equals 2 partition function, or more generally to the von Neumann entropy. Now, I'm drawing these pictures as if they're Lorentzian black holes, but actually, to be more precise, you should think of these as Euclidean path integrals that have been continued into Lorentzian time. That is, they're defined in Euclidean and then analytically continued. Or you could think of these as Schwinger-Keldysh style in calculations with a Euclidean part that prepares the initial state and then a Lorentzian part that evolves the initial state in time. Here I've drawn an example of what some of these wormholes look like in Euclidean signature. Now, assuming a symmetry, so the next thing we need to do is we need to do this for all n, is for all replica numbers, and then we need to continue to n equals 1. That sounds hard, but it's actually not so bad, because if we assume that there's a cyclic symmetry permuting the n replicas, then you can phrase this problem where, in a way that so once you reduce out by that symmetry, you get a problem that can be considered an arbitrary real n. And then you can take n to be a non-integer. So once we've done that, we can calculate the von Neumann entropy. Remember, our replica formula was that the von Neumann entropy S is minus z prime of 1. So now that we've constructed these saddles for all n, we can ask what happens to the saddles near 1. And what happens is that the mouth of the wormhole becomes the island as we take n to 1. And the path integral on this continued wormhole gives you the island formula for the entropy. So if we go back now to the Page curve, then, so remember that the dashed line was Page's proposal for what the entropy should look like in a unitary evaporating black hole. In view of islands and replica wormholes, here's how we now interpret that. At early times, there is no island. In terms of the replica wormholes, there is no replica wormhole, or if there is, it's subdominant. So the Hawking saddle dominates, and the dashed line at early times agrees with Hawking's calculation, where the entropy just increases with time. But then at the Page time, which is this sharp transition point, the wormhole saddle starts to dominate. So there's an exchange in dominance, just as I was describing, when the Hawking saddle contribution gets so exponentially suppressed gets exponentially suppressed by this large entanglement. At that point, the wormhole saddle takes over, and its entropy is given by the black hole area over 4. So there's a transition between these two saddles, and it's that transition that's responsible for the sharp transition in the Page curve. Okay, so that's the basic review of islands and replica wormholes, and I'm going to conclude now with just a couple of remarks. First of all, a question: does this show that black hole evaporation is unitary? Well, it is evidence in this direction, but no, it does not show that black hole evaporation is unitary. So why not? Well, we've calculated the S of the radiation. And we used a shortcut. We used the Euclidean path integral to calculate this entropy of the radiation without calculating the density matrix itself. And because we've used Euclidean methods to calculate this, we haven't even shown that a rho sub r exists, which has this entropy. In other words, we've calculated the left-hand side of this equation, but we haven't shown by this Euclidean method. But that method sidesteps the question of how rho sub r itself evolves, and whether there is even a rho sub r that obeys this equation. To make this sound more familiar, I would say conceptually this is on exactly the same footing as the Euclidean calculation of the black hole entropy by Gibbons and Hawking. So they used the Euclidean black hole, calculated its on-shell action, and extracted from that the black hole entropy. And from that, they found the entropy of the black hole is the area over 4. We believe this gives the right answer, but it certainly doesn't exhibit the microstates. In other words, it tells you what the entropy should be, but it's a macroscopic calculation of that entropy. It's not really a microscopic calculation. It doesn't even tell us whether those microstates really exist. That's presumably something that you have to go to string theory to answer. And I think the Page curve is on a similar footing. Second question I want to ask very briefly is, do wormholes imply averaging? There are other situations, not quite replica wormholes, but very similar situations, where wormholes seem to violate some of the basic properties of quantum mechanics. The reason for that is that once you include extra bridges in your geometry, like you have here, then your amplitudes and your calculations no longer seem to obey the factorization properties that we expect in a quantum mechanical theory. Okay, so this is something that has sparked a great deal of discussion. I won't try to get into that. I just want to mention it. And I would say that there are roughly 3 possible interpretations of how to deal with wormholes and averaging. One is that we take averaging seriously, that gravity is an average over microscopic theories. This is very surprising, but it's exactly what happened in this duality of Saj-Shenker and Stanford between JT gravity and random matrix theory. So maybe we should take that very seriously. The second option is that we reinterpret this average as being one bigger quantum mechanical theory that obeys the ordinary rules of quantum mechanics, but has superselection sectors corresponding rather to the different members of the ensemble that one would average over. So there's an old story going back to Coleman, and in this context has been explored and explained by Marolf and Maxfield, that these 2 points of view are actually essentially equivalent to each other. You can interpret this average in terms of superselection sectors, and that way you don't have to give up quantum mechanics. What you do then have to confront is enlarging the Hilbert space of quantum gravity. So once you've included these extra bridges, you have to allow for a Hilbert space of multiple universes. So this is called baby universes. Option 3 well, I would describe this one as saying that wormholes appear only in the infrared. In other words, that wormholes appear in this calculation, but that if you were able to do the calculation in the UV complete theory, there actually would be no wormholes and no problems with factorization, and it would just be an ordinary quantum theory. Skeptics of option 3 would argue that this requires magical cancellations in order to get the wormholes to go away as you consider the complete theory, but maybe those magical cancellations are real. There are, after all, plenty of other cases where requiring a quantum theory of gravity to be consistent requires magic cancellations, and those cancellations do occur in consistent theories. Okay, and this is my last slide. I think it seems like a good time to revisit the idea of quantum cosmology in light of islands, replica wormholes, and more generally, the idea that higher topologies are important. Why is that? Well, a crucial ingredient for wormholes or islands was this large entanglement. We found that the large entanglement suppresses the Hawking saddle and makes the wormhole saddle dominate. That was one way of thinking about it. Well, cosmology also has situations with large entropy or large entanglement. There's the large entropy of the de Sitter horizon in the early universe or late universe. There's the fact that cosmology has entropy proportional to area and therefore, proportional to volume. And therefore, you can always get a large amount of entropy just by taking a large enough volume. So this poses a question: are wormholes important in cosmology? And I will leave you with that question. Thank you.